Welcome, everyone. So glad you could join me for this explainer on safety engineering. Today, we're diving straight into Chapter 12 of your software engineering syllabus, and we'll specifically be looking at the Introduction to Safety Critical Systems. You know, as software engineers, you'll soon realize that your code doesn't just, run inside a vacuum. It interacts with the physical world in very real ways. And in many cases, it plays an absolutely critical, life-saving role. So, let's jump right into this and explore how we engineer software that literally preserves human life. To kick things off, I want you to consider a question that might sound a bit contradictory at first. Can a software program execute perfectly, flawlessly even, and yet still cause a catastrophic crash? Well, picture this. It's September 1993. A passenger plane is landing at Warsaw Airport in Poland during a massive, severe thunderstorm. For 9 agonizing seconds after touching down, the computer-controlled braking system simply did not engage. The plane ran right off the end of the runway, hit an earth bank, and caught fire. But when investigators finally analyzed that crash, what they found was astonishing. The braking software, it had executed reliably. It behaved exactly according to its specification. But the specification itself was incomplete. It hadn't accounted for the rare physical conditions of that specific storm landing, so the program worked perfectly, but the system still failed catastrophically. Okay, here's our roadmap for today's explainer. We're going to start by untangling reliability versus safety. Then we'll look at why reliable systems actually fail. From there, we'll define safety-critical systems, unpack the engineering toolkit for hazard management, discuss something called normal accidents, and finally, wrap it all up with an exam-focused summary to prep you for your tests. Right, let's get into Section 1, reliability versus safety, and understanding that core distinction. It's really common for young engineers to just assume that a reliable program is inherently a safe program. But as we just learned from that Warsaw crash, this is a super dangerous misconception. So first, let's isolate and define reliability. Reliability is simply the probability over a given period of time that a system will correctly deliver services as expected by the user. What does that mean in plain English? It means the system executes exactly what it was programmed to do. If the spec says do X when Y happens, a highly reliable system is going to do exactly that, every single time, without freezing or crashing. Safety, on the other hand, is a completely different beast. Safety is a judgment of how likely it is that the system will cause damage to people or its environment. It is specifically about preventing catastrophic failure, death, or injury. Notice something there. That definition doesn't care one bit about the software specification. It only cares about the physical outcome in the real world. And that Warsaw crash brilliantly synthesizes this difference for us. Reliability is all about meeting specifications. Safety is all about preventing harm. In that runway crash, the software met its specification because a built-in safety feature actually stopped the reverse thrust from deploying. Why? Because based on the sensor readings in the storm, the software assumed the plane was still airborne. So the software was highly reliable, but because the specification didn't account for the reality on the ground, it was completely disastrously unsafe. You absolutely can have a perfectly reliable system that is completely unsafe. Moving on to Section 2, let's look at 4 critical reasons why reliable systems fail. So, the big takeaway so far is that reliability is necessary for safety, sure, but it is definitely not enough on its own. Now that we've got that down, let's explore exactly why a supposedly reliable system might still fail us. There are 4 main reasons. First up, hidden, dormant bugs. We can never, ever be 100% certain that software is entirely fault-free. A bug might literally lay dormant for years before a very specific set of conditions triggers it. Second, incomplete or incorrect specifications. Third, hardware malfunctions. That's where the physical components behave unpredictably, sending completely wrong signals to the software. And fourth, operator error. Put simply, humans just doing the wrong thing. Now, what's really fascinating and slightly terrifying is our second point, incomplete specifications. I really want you to remember this because studies consistently show that difficulties with requirements and incomplete specifications are actually the most common root cause of safety-related software errors. Just like our Warsaw runway incident, if the engineers fail to anticipate a rare physical situation, well, the software simply won't know how to handle it safely, no matter how beautifully flawless the code is written. Let's look a bit closer at our fourth point too, operator error, with a pretty incredible real-life anecdote. Once, an aircraft's undercarriage just collapsed while the plane was parked safely on the ground. Why did that happen? Well, a technician accidentally pressed a button instructing the utility management software to raise the landing gear. The software carried out the human's instruction perfectly. It was incredibly reliable, but it was deeply unsafe because the software just blindly obeyed a highly dangerous command. It totally lacked the safety checks to say, hang on a second, the plane is on the ground, I should probably ignore this command. Section 3. Defining safety-critical systems. These are the systems that preserve life. We've seen that hidden bugs, bad specs, hardware failures, and simple human errors can compromise even the most reliable software. Which brings us to the formal taxonomy of systems where we absolutely fundamentally cannot afford these failures. We call these safety-critical systems. Let's define it clearly. Safety-critical systems are systems in which it is essential that system operation is always safe. Specifically, a failure in these systems could cause death, injury, or severe environmental damage. Because the stakes are literally life and death, we divide these into two subcategories to better understand how to engineer them. Those two categories are primary safety-critical software and secondary safety-critical software. Primary software acts directly as a controller within a system. If it malfunctions, it directly and immediately causes a hardware malfunction that results in human injury. Secondary software, however, is software that can only indirectly result in an injury. It's not controlling the deadly hardware directly, but its outputs or data can lead to catastrophic downstream effects. Let's look at some real-world examples to make this concrete. A classic primary system is a software-controlled insulin pump. If the pump's software calculates the wrong dose, it injects an overdose directly into the patient's bloodstream, causing immediate physical harm. The software is the direct controller. Now contrast that with secondary systems, like computer-aided design or CAD software. If CAD software has a bug and calculates a bridge's load capacity incorrectly, that bridge might collapse 10 years later. The software didn't physically knock the bridge down, but it indirectly caused the failure. Another great example is the MentCare software used for mental health patient records. If it fails and a doctor doesn't see a patient's critical warning notes, that unstable patient might be mistakenly released and injure themselves. It's an indirect but absolutely vital safety link. All right, Section 4, Hazard Management Strategies. Let's open up the engineering toolkit. Okay, so we know what these systems are, and we know exactly why they fail. The real question is, how do we, as engineers, actually build them to prevent these disasters? Think of this next section as your critical toolkit for your future engineering careers. When we design safety-critical systems, we use a hierarchy of 3 distinct hazard management approaches. Step 1 is hazard avoidance. Step 2 is hazard detection and removal. And Step 3, when all else fails, is damage limitation. Let's break each of these down. Step 1 is hazard avoidance. And frankly, this is the gold standard. Here, you design the system so the hazard is just fundamentally impossible. For example, think of a massive industrial paper cutter. A major hazard is the operator's hands being under the blade, right? So how do we avoid it? We design the machine so it physically requires the operator to press 2 completely separated buttons simultaneously using both hands just to bring the blade down. By design alone, we have entirely avoided the hazard of a hand being in the way. But let's be real, we can't avoid everything, and that is exactly where Step 2, hazard detection and removal comes in. This is all about catching a hazard before it becomes a full-blown accident. Say, in a chemical plant, you might have a software system that detects excessive pressure building up in a giant tank and automatically opens a relief valve to safely vent the gas before an explosion can occur. Finally, Step 3, damage limitation. If the worst happens and the accident occurs, how are we minimizing the fallout? An aircraft engine catching fire is a severe accident, but modern aircraft engines have automated fire extinguishers built right in. The accident occurred, yes, but the damage is limited to just one engine, ultimately saving the plane. Section 5, the normal accidents theory. What happens when 100% safety is impossible? So despite all these incredible hazard management strategies we just talked about, I do have to introduce a pretty sobering reality check regarding highly complex systems. The sociologist Charles Perrow coined this concept called normal accidents. He argued that in highly complex systems, accidents are actually inevitable. Why? Because as systems grow in complexity, we simply cannot predict every possible combination of simultaneous failures. For instance, if an air conditioning unit fails, a server might overheat, which might send a corrupted signal to the software, which might confuse the human operator into making a fatal error. We are great at engineering for single points of failure, but we cannot predict unanticipated, cascading interactions across hardware, software, and unpredictable human behavior. Therefore, according to Perrow, 100% safety is just impossible. And that brings us to Section 6, Summary and Exam Focus. These are your essential takeaways. All right, everybody, pens ready, listen up closely. I am verbally flagging this summary as an exam focus because this stuff is highly likely to appear in your upcoming tests. First, you absolutely must be able to explain the difference between reliability, which is executing the program exactly as specified, and safety, which is preventing harm in the real world. You need to know the 4 reasons reliable systems fail: hidden bugs, incomplete specs, hardware faults, and operator error. You must be able to categorize systems into primary controllers, like insulin pumps, versus secondary systems, like Monocare. And finally, you have to understand the 3 hazard management strategies: avoidance, detection, and minimizing damage. Now, let's walk through these 3 final definitions deliberately, because getting these right is a guaranteed way to secure marks in your exam. Write these down. A hazard is a system state that could lead to an accident. It's the potential for danger. An accident is the actual catastrophic failure causing death or injury. And risk is a measure of the probability that the system will cause that accident, taking into account just how severe the hazard is. Memorize these 3 definitions for sure. To wrap up today, I want to leave you with a bit of a provocative thought. We just established with the normal accidents theory that 100% safety is impossible. Yet software controls somehow allow for vastly more sophisticated safety monitoring than old, clunky mechanical systems ever could. So how exactly do we bridge that gap? How do we write the specific requirements to make our software as a robust, life-saving safety net? Well, that is exactly what we will be exploring in our next lecture on safety requirements. Thank you so much for joining me for this explainer, and happy studying.